I will determine the irreducible representations of the 4 ligands surrounding a transition metal with a tetrahedral point group. In the character table of the tetrahedral point group, we can find a total of 24 symmetry operations. This letter E stands for identity element. It means doing nothing, so we don't do anything. And over here we have 8 C3 symmetry operations. Actually, there are only 4 threefold rotation axis. 1, 2, 3, 4. Or if you look at this permanganate structure, 1, 2, 3, 4. 4 threefold rotation axis. Why 8 symmetry operations? Well, you can rotate this transition metal complex about this C3 axis 120 degrees or 240 degrees. Therefore, each C3 element corresponds to 2 C3 symmetry operations. And then you have 3 C2 symmetry elements and also 3 C2 operations. So this is one of the C2, okay, right here, this C2 axis. Okay, there are 3 of those. And then you have 6 S4 symmetry operations. S4 is a improper symmetry axis or operation. So if you're looking at a S4 symmetry element, it means you rotate the structure 90 degrees followed by a reflection with respect to a symmetry plane that's perpendicular to the C4 axis. All right, so actually there are only 3 S4 improper rotation axis in the molecule. Okay, but again, why do we have 6 symmetry operations? So basically it means, well, again, I'm going to show you one of the S4 improper axis. So this one. Okay, the same as the C2 rotation axis. This is also S4. So basically you can rotate this transition metal complex structure 90 degrees followed by a reflection, and you get the same structure. You have the same kind of atoms on the same positions, right? But then why 6 S4 operations versus only 3 S4 elements? Well, for each S4 symmetry element, you may rotate the structure 90 degrees or 270 degrees followed by a reflection. Okay, so what about 180 degrees? Well, if you rotate the structure 180 degrees followed by a reflection, that's equivalent to the inversion center, and we don't have that in this structure. And then we have 6 sigma D symmetry planes and also 6 sigma D symmetry operations. Why do we have 6 such symmetry planes? So there are 4 ligands here, 1, 2, 3, 4. Actually, you can imagine there's 1 sigma D that contains these 2 oxygen atoms, a second sigma D that contains these 2 oxygen atoms. Okay, the third sigma D contains these 2 atoms, the fourth these 2 atoms, the fifth these 2 atoms, and then the sixth sigma D contains these 2 oxygen atoms. All right, therefore you have 6 sigma D symmetry elements and 6 sigma D symmetry operations. Again, 5 different types of operations, but if you count the total number of symmetry operations, that's actually 24. You have 1 here, you have 8 here, 3 C2 operations, 6 S4 operations, 6 sigma D operations. If you sum it up, over here, I'm going to just use the sum function here, equals sum from B1 to F1, that's 24. And 24 is the order of the tetrahedral point group. We can get this number 24 in a different way. If you look at the 5 irreducible representations here, A and B's, okay, we don't have B here, but A's and B's have a degeneracy of 1, E means a degeneracy of 2, and T means a degeneracy of 3. Unfortunately, we use the same letter E for a degeneracy of 2 and also for identity symmetry element. Okay, this is very unfortunate. We're using the same letter E for 2 different meanings. Okay, but yeah, we'll just accept that. And if you square this character, okay, and then this one, and then this one, and this one, and this one, you get 11499. So they are here. And then you sum up the squares of the 5 characters in the column of identity symmetry element, you get 24. All right. And again, this 24 is the order of the tetrahedral point group. In this character table, I use red color for every single negative characters. So you have a bunch of negative ones here and there. All right. To really visualize those symmetry elements and symmetry operations, I recommend you to use the symmetry.otabine.edu website to rotate the molecule to see those symmetry elements and operations. All right. If we have 4 ligands, again 1, 2, 3, 4 ligands, it's tetraoxydo manganate, or the common name permanganate. It has 4 identical ligands here. Okay, and then if we do a E operation, that means doing nothing. All 4 ligands remain in their original positions. So the number of ligands that remain in original positions is 4. So we put 4 here. What if we do a C3 rotation? Either 120 degrees or 240 degrees, because this C3 axis, okay, passes through one of the 4 ligands. Again, just either this one or this one, just one of the 4 ligands. The other 3 ligands will move away from their original position. So only one ligand remains in its original position. So I put a number 1 here. C2. So if we rotate this structure 180 degrees about this twofold rotation axis, all 4 oxygen atoms will move away from their original position. So therefore I put 0 here. Similarly, 0 here. Again, if you do a S4 operation, all 4 oxygen atoms will move away from their original position. Actually, this oxygen atom will move to here. This oxygen will move to here. All right. And then the last one, sigma D, that's just a symmetry plane that contains 2 of the ligands. So for example, maybe this symmetry plane that contains this oxygen atom and this oxygen atom. So if you do a reflection, these 2 atoms are not moving, but these 2 will switch their positions. So 2 ligands, these 2, will remain in their original positions. So I put a number 2 here. All right, and then we have 5 numbers here. We multiply these 5 numbers with this 5 numbers here. Those are the number of symmetry operations for each class of symmetry operation. So 5 different symmetry operation classes 5. 1, 2, 3, 4, 5. 5 columns, 5 rows. Okay, and each class has a different number. Okay, 8, for example, 8 different C3 symmetry operations. So we multiply these 5 numbers, the number of ligands that remain in their origin positions, with these 5 numbers. Again, that's the number of symmetry operations. All right, and we get the products here. So I'm gonna make this spreadsheet a little smaller so that we can see this row of 5 numbers multiplied by this row of 5 numbers. You get the 5 products respectively. So 4 times 1, you get 4. 1 times 8, you get 8. 0 times 3, you get 3. So basically, I'm using an Excel function here. It's just a multiplication function, and then we can kind of drag it horizontally. And the last one is 2 times 6, you get 12. We're not done. We get these 5 numbers. We then use these 5 numbers, okay, multiplied by each of the 5 rows. So we have 5 rows, 5 irreducible representations. We have 5 rows. So each of the 5 rows multiplied by these 5 numbers. Again, I'm going to give you an example here. Let's look at A1. 1, 1, 1, 1, 1 multiplied by these 5 numbers, and we get the same 5 numbers, and then we sum it up. The sum of the 5 numbers is 24. And then 24 divided by the order of the tetrahedral point group, we get 1. That means the 4 ligands form one A1 irreducible representation. How about A2? We look at the characters of this A2 representation. It's 1, 1, 1, negative 1, negative 1. So again, this 5 numbers multiplied by these 5 numbers. Okay, and we get a negative 12 here, and we sum it up. We get 0 divided by the order. We get 0. That means we have 0 A2 irreducible representation. The last example, I'm going to look at T2. Those are the 5 characters for the T2 irreducible representation. So these 5 numbers multiplied by these 5 numbers correspondingly. Okay, again, I'm going to just click this. You can see it's just a multiplication. This number 4 times 3, you get 12. And then I'm going to just drag it from left to right. Okay, and then I'm going to sum it up. There are 5 numbers. The sum is 24. So again, the sum is 24. Divided by the order of the tetrahedral point group, we get 1. That means we will have 1 T2 irreducible representation. So basically, if you have 4 ligands in a transition metal complex, they can form 1 A1 and 1 T2. T2 is triply degenerate. Okay, why is this important? Again, we need to look at the character table. So we have A1 here. A1 is totally symmetrical. So that means, well, if you have 4 ligands forming this A1 irreducible representation, the 4 ligands will interact with a totally symmetrical atomic orbital on a transition metal. In this case, this permanganate, the 4 ligands will interact with the 4s orbital of this transition metal. How about T2? Okay, if we look at the character table, we see XZ, YZ, XY. They correspond to actually the DXZ, DYZ, and DXY orbitals on the transition metal. So the 4 ligands can form a T2 irreducible representation, and they will interact with the DXZ and DYZ and DXY orbitals of the transition metal. And the interaction will actually push up the energy level of the 3D orbitals. the interaction will make this 3d orbitals anti-bonding orbitals. All right. And then what about the other 2d orbitals on the transition metal? They are dx squared minus y squared. It's over here. The last one is dz squared. So the proper name for dz squared should be actually d sub 2z squared minus x squared minus y squared. That's actually the proper naming for dz squared. But this is so complicated, so people usually just say dz squared. In most textbooks, you see dz squared, but really it's actually 2z squared minus x squared minus y squared. And then these two d orbitals are degenerate, okay, with a degeneracy of 2. However, these 4 ligands, either in this permanganate or any other tetrahedral transition metal complex, the 4 ligands cannot form a irreducible representation. Therefore, these 4 ligands will not interact with dz squared or dx squared minus y squared. So these two d orbitals will become non-bonding orbitals in the transition metal. Again, these 2 non-bonding, these 3 anti-bonding. Okay, you will observe the splitting of the energy levels of the 5d orbitals here. Well, does it have to be transition metal complex? No. You can use the same analysis for CH4. All right, so if you have CH4, you have 4 hydrogen atoms. Each one has a 1s atomic orbital, and you can do a similar analysis of the symmetry of the 4 1s orbitals. And you will see the 4 1s orbitals can form A1 irreducible representation and a T2 irreducible representation. And the A1 irreducible representation will interact with the 2s orbital of the center carbon. Now imagine this is carbon surrounded by 4 hydrogen atoms. Okay, what about the T2 irreducible representation formed by these 4 hydrogen atoms? Well, it will interact with the px, py, and pz atomic orbitals on the carbon atom. Okay, so you can use the same analysis for a organic chemical molecule as well. Get back to transition metal chemistry. So we did mention that these 2 dz squared and dx squared minus y squared orbitals on the transition metal center will not interact with the 4 ligands. Therefore, those are non-bonding orbitals. Okay? And then dxz, dyz, dxy will interact with the 4 ligands and become anti-bonding orbitals. The lone pair electrons of the 4 ligands will become bonding molecular orbitals. So you have bonding molecular orbitals, you have anti-bonding molecular orbitals. All right, and we're not completely done yet. These 3 anti-bonding molecular orbitals will further interact with the px, py, and pz atomic orbitals of the same transition metal. It sounds bizarre, but there's some mixing here because this dxz, dyz, dxy have this T2 symmetry. Px, py, pz on this metal also have this T2 symmetry or irreducible representation. So these 3 d orbitals can mix with the 3 p orbitals. And the mixing can actually slightly lower the energy of these 3 anti-bonding orbitals. Therefore, in transition metal chemistry, you'll see, well, these 3 d orbitals become anti-bonding orbitals. These 2 d orbitals become non-bonding molecular orbitals in the transition metal complex. But the energy difference between these 3 d orbitals and these 2 d orbitals is smaller than that in a octahedral transition metal complex because of the mixing between the 3d orbitals here and the 3p orbitals here.